WMAP satellite measured this to this kind of accuracy, which was unprecedented at the time. So they're kind of it's called the premier baryometer. So they measured the amount of matter better than anything else before. Is there any questions on that? Okay, so direct detection of dark matter. So like I said, it's believed to be possible. So the search is on right now to find this stuff through two different mechanisms. One is with these particle accelerators. They're trying to just basically create it in the accelerator. It's one of the things they're hoping that will come out of these experiments. And the other is that we're just going to have passive detectors around here that are going to collect this stuff as it passes through the Earth. This is what's thought to be the way that's going to find dark matter. And basically, the basic idea is that the dark matter particle is basically zooming in from the cosmos. It just so happens to crash into a particle that we know, and then that interaction, so it causes that particle, say, to bounce, or it causes the electron to move in that particle, and then we can observe that interaction. So the whole idea of it being dark matter is we can't actually observe the particle, but if it crashed into our detector, we might be able to see the interaction that's going on there. And that's the basic idea for detecting these things. So this requires extremely precise measurements. So like if it's happening the way we think it is, it's passing through our body all the time right now, every once in a while it's having an interaction, but we don't know. We don't see it because it happens very, very low, and it happens way less than cosmic rays and things like that. So you need to get really low levels of background radiation. So to do that, what physicists do is go into extremely clean areas to do this. So I'm going to talk a little bit here about SNOLAB. This is the Canadian Institute for Particle Astrophysics, and that's where they study this kind of stuff. SNOLAB is a class 2000 clean room. So what class 2000 means is that there's less than 2,000 particles of a half micrometer or larger permitted per cubic foot of air. So to give you an idea how clean that is, that's a million. Normally there's a million times. It's class a million, which is 500 times more particles. So they go there, and then the major thing that they do to reduce the background is they go underground. So SNOLAB is located 2 kilometers underneath Norway rock, which corresponds to 6,000 liters of water, and that's just the density calibration. So that's how they calibrate all the labs around the world, is by comparing it to how much water it would be. So to give you an idea how deep that is, this is a kind of good image. There's a CN Tower. We all know how big that is, and it's basically almost 4 CN Towers deep. That's how far down they go. And this is necessary to reduce the background radiation in order that you can see this dark matter stuff. So just a little bit more about SNOLAB. This 2,073 meters results in about a 50 million time reduction in the cosmic rays. So I said, to observe this dark matter, we have to get rid of the background noise, and this reduces that noise down by 50 million times. So hopefully that'll allow us to observe dark matter. This corresponds to 1 cosmic ray every 3 days to the experiment. So really, it allows you to kind of see these things, each specific one, and that we can calibrate them and study them. And SNOLAB is currently the world's deepest underground laboratory. One is in construction in the US now that is going to be almost 3 kilometers deep. But they're like 10 years behind us, so we might be first. SNOLAB, what they're studying is predominantly neutrinos and dark matter. So I said it's particle astrophysics. Those are the major particles in particle astrophysics. So low energy solar neutrinos is looking specifically at what's going on at the core of the sun, the nuclear reactions that are going on. Neutrinoless double beta decay is basically looking at the matter-antimatter properties of neutrinos. So it's just an experiment that's going to see if neutrino is its own antimatter particle. Dark matter searches is what is prevalent to us, and supernova neutrino searches. So one of the things about a supernova is that right before it explodes, it is going to release a lot of neutrinos. So we have certain detectors located throughout the world that are watching for these things, and if they see a large neutrino flux coming from a specific point in the sky, they're going to alert basically all the telescopes across the planet, and everyone's going to be looking at this supernova. So it's just a watch, so that way we can study supernovas, because they go off like very infrequently, like 1 every 100 years in our neighborhood is what it's thought, and one hasn't occurred in 400 years. So everybody wants to find one of these things to observe. So there's a lot of mechanisms in place to make sure we don't miss the next one. So that's going on in SNOLAB too. So related to dark matter, the current projects. So Picasso is the project in Canada to search for supersymmetric objects. So like I said, WIMP is a SUSY particle. And what they basically do is they have a cylinder of Freon, and it's superheated. It's a superheated critical fluid. So basically, if a dark matter particle crashes into it, it's going to cause a vibration that's going to result in a lot of sound passing through this stuff. And then they have little speed amplifiers that are going to pick this stuff up, and then they're going to study dark matter that way. Deep 1 is the experiment that I worked at on SNOLAB. So it stands for Dark Matter Experiment with Argon and Pulse Shape Discrimination. Basically what that means is that it's a tank of liquid argon, and the way, when like I said, that dark matter particle, when it hits an argon atom, it's going to result in a specific effect, and we're going to observe the light from that effect. So pulse shape, we're going to see what this light does. So a dark matter particle is going to correspond to a really sharp peak of light and then a really quick decline. You'll see that light. Whereas a cosmic ray or a decay of the argon is going to correspond to a slower increase in the amount of light that we see and then a decline again from that reaction. So you can pulse shape discriminate these two things, and that's how DEEP is going to try and find dark matter. Under construction are DEEP 3600. So DEEP 1 is actually the prototype for this thing. DEEP 1 is 7 kilograms of argon. DEEP 3600 will be 3,600 kilograms, over 3 tons of argon. So it's going to really increase the sensitivity to dark matter, and that's under construction. That's in the lab right now. And also mini clean. Clean is cryogenic low energy, something with no bug gases. And basically they're using almost the exact same idea as DEEP, where they have this noble gas. They're probably going to use argon, and then they'll observe the effect of the WIMP crashing into the noble gas. In the long term, they are hoping to have more Picasso experiments, so Picasso's upgrading. They have currently, well, when I was there, they had 28 of these things, and they're about to go up to 40, so this was going to increase their sensitivity. So I said their mini clean was going in, and that was 1,000 kilograms. The clean, the full out experiment, is going to be 1,000 tons. So another 10 to the 3 times as much matter and way more sensitivity. Another one is cryogenic dark matter search, CDMS, and they're currently the world leaders in terms of sensitivity. Not by much, but they're leading the world. One of the ways that they're going to up their sensitivity, they're really trying to up it because they think they're getting close. One of the ways to do that is to reduce their backgrounds, which they can do by coming to SNOLAB, because the facility they're at right now is not as clean as SNOLAB. And another one, I think the one I had there is xenon, which is another variant of the noble gas idea. So just to conclude, what we talked about today was why do astronauts care? So hopefully, this was a good half an hour for you. We talked about what reasons do physicists think that dark matter is out in our universe. What's the lines of evidence? We talked about what are some of the explanations for this observed discrepancy in matter. And we talked about the scope. So we know it's pretty prevalent throughout the universe. We see it everywhere. It's pretty much homogeneous throughout. And then we just basically highlighted some of the ways that physicists are currently trying to detect it. So thanks.